the table with frequencies or counts. You could fill them in with proportions or relative frequencies, but for the sake of this test, we're going to put counts in there, okay? So for example, that 33 says that there were 33 observations that had this outcome, A1, and this outcome, B2, simultaneously, okay? So let's say, let me try to think of something. Let's Price is Right wise, okay? Oh, the Take Two game. Take Two game is when you have to pick two prizes that total a certain total. And if you win, you do it on the first time, you win. So A1 and A2 could represent, did you, well, this is a bad example. Okay, the point of the matter, I can't think of an example right now, but the point of the matter is that these 33 observations had this particular outcome for A, we'll call it A1. This particular outcome B2 for event B, okay? And now we got to talk about new notation. In the last lecture, we talked about OI, which is the observed frequency for the ith class, okay? But now we got to say OIJ. This is the observed frequency for the ith row and the jth column. So for example, this is 012, the notation for that storing where we will store this value in. This is 012. 012, first row, second column. Is everybody with me so far? So for example, 91 would be what? 02, 1. Second row, first column. 021.
And then 022.
022 would be what? 12. Is everybody with me so far? So 011, 012, 021, 022. Okay? That would be the notation, the variable notation that will store these values. Take a look here. Who said that we had to have a 2 by 2? This, by the way, this is a 2 by 2 contingency table. 2 rows, 2 columns. Take a look here. How many rows are in that contingency table? 2
by 4.
And how many? 2 by 4. So the dimension of that contingency table is 2 by 4. The way we'll write that is, so the dimension of that contingency table would be 2 by 4. Is everybody with me so far? All right. What is the notation for the value of 11? So this 11, what is the notation for that? What row is that in?
2.
Second row,
4.
fourth column. So what would be the notation for that? 024. That's correct. And the 2 and the 4 would be the subscript. Okay, so 024. That's right. So that 11 would be 024. So what is 013? What's the value of 013?
28.
28. That's correct. First row, third column. 28. That's right. By the way, what do you think that's a contingency table for my Price is Right fans in here? What do you think this represents?
Like
What pricing game?
Wheel? No, it's not the wrong one.
spinning.
No, it's not. Cause
Just seeing if you, for any Price is Right fans in here. And that, by the way, that's real data. That's real data. The grand game. The one where you have to pick the 4 prizes, the products that are less than a certain amount of value that they give to you. You go from $10, $100, $1,000 to $10,000. That's the grand game. So, okay, that bored you. Okay. So yeah. So this is a 2 by 4 contingency table. Remember, when you talk about the dimension of the contingency table, you don't include the total row or the total column. Is everybody with me? Only where the observed frequencies are. So 2 by 4. Okay. All right. So like I told you, the reason why we need to do a review on contingency tables because that's important for knowing how to calculate the observed test statistic. And we're going to need to know that because we need to talk about degrees of freedom. Just like when we did the goodness of fit test, degrees of freedom, right? We talked about with the chi-square distribution. These two chi-square tests we're going to cover involve the chi-square distribution, and we have to calculate degrees of freedom. That is depending on the dimension of the contingency table. Okay. All right. By the way, when we did the chi-square goodness of fit, and we were dealing with, let's say, I'll just create something really quick. I'll just say money one. So let me go back to this one. If I wanted to make that into a frequency table, like this, what values would go here?
No.
If I want to turn that from a two-way contingency table, from a two-way contingency table to just a frequency table.
Oh, you would add no zero to it?
That's right, which is what you were saying too, right? So what value would go there?
6.
6. What value goes there?
13.
13. What value goes there?
46.
46. Now I'm going to get ready to ask you a very tough question to see if anybody remembers this. What value goes there? No, it's not this question. Obviously, this is what?
18.
18. Now, here comes my tough question, okay? What did we do to the data when we went from two variables? These are two variables we were interested in, gender and how much money you won on the grand game, to just one variable, just how much money you won, okay? One. I just went from two variables, being interested in two variables at the same time, to just one variable. What did we do to the data? We blanked it. Here's the tough question. What is the term we did?
Consolidated?
It's synonymous to the word consolidated, but it starts with A. Say it then. Oh, it starts with the letter A. A, G,
Aggregated.
Aggregated is the correct answer, yeah. We aggregated the data. When you consolidate the data like that, when you combining values together, you're what's called aggregating. Is everybody with me? Now, if we started with this data and we then broke it down into that data and turned it into that way, going that way, okay, going this way is aggregating. Going that way is what? What's the term for that? If this way is aggregating, shrinking, that's aggregating.
De-aggregated?
Not de-aggregated, but
Unaggregated?
starts with D.
Disaggregate?
Disaggregated, correct. When you break it down into multiple counts, when you go from here to here, that's called disaggregated. Write that down, okay? That's called disaggregating the data, okay? You break down the data further, that's disaggregating, okay? But when you concatenate, when you combine or consolidate, going from here to here, that's aggregating the data, okay? All right, questions so far? Make sure you get what we just finished talking about. I told people write it down. Bro, I hope you wrote that down. But you probably want to write it down. If you sit on the final, don't say I didn't teach it to you. Okay? All right. So, I was leading to something. If we were to do the chi-square goodness of fit test on this, how do we determine the degrees of freedom? Y'all remember? How many rows do we have? How many classes do we have?
4.
4. So what was the degree? If we were to do a chi-square goodness of fit test on this, what would be the degrees of freedom? 3. It's the number. It was k minus 1. K is the number of classes, right? So it's 4 minus 1, which is 3. What do you think? So tell me, without me showing you yet, how would we calculate the degrees of freedom for this data? If we were to do a chi-squared test with this using the data from this contingency table, what do you think the degrees of freedom, how will we calculate degrees of freedom? We have two variables now. We have gender and we have how much money was won. Is everybody with me so far? And so how many classes are with this variable? How many classes are there? 4. So 4 minus 1 is?
3.
We have another variable though, gender. There are how many classes? 2. 2 minus 1, which is?
1.
What do you think the degrees of freedom is?
The average.
1.
1. 3 months.
2.
How many
Two.
of you say it's 1? How many of you say it's 3? How many of you say that it's neither of these?
Is it 2?
I'm gonna tell you what it is. It's 3. You have to multiply.
Oh.
1 times 3 is 3.
Oh, that makes sense.
You see what I'm saying? Yeah. So you're gonna multiply the degrees of freedom for this case, which is 1, times the degrees of freedom for that case. So 4 minus 1, which is 3. 2 minus 1 is 1. 3 times 1 is 3. Degrees of freedom for that example, this example would be 3. Is everybody with me so far? We'll see it later. I'm just trying to foreshadow. I'm just foreshadowing right now. Okay? So we're going to see that when I show you the 5 steps of the hypothesis test. Okay? Let's start with the test of homogeneity, because this will be an excellent example of a demonstrated test of homogeneity. Let's go back to this before we talk about this. So we have the results of Price is Right contestants playing the grand game. In the grand game, someone can win $10, $100, $1,000, $10. Actually, somebody can win 0. There's a possibility you win 0, but I didn't include that data. And then we have the contestants broken down by male versus female. What do you think? Tell me what you think I could analyze using this data. Obviously, I have male versus female, so I must be what? Between the two groups. I must be, starts with C, comparing the two groups. That's the word I was looking for, comparing. I must be comparing males to females. Is everybody with me? In terms of their performance playing that pricing game, right? Now, there are lots of things I can do with this data, okay? But I'm gonna tell you what we're gonna do. We want to determine whether or not if the amount of money won is dependent on gender. Does any particular gender tend to do well in this game more than the other? Is everybody with me so far? So for example, look here. Looks like to me, let's say 29. Or how about this? Let's just look at 10,000. That's the big amount. 11 divided by 41. That's close to 10 divided by 40. So that's about 25%. 7 out of 42, though, that's 1/6. That's 16%, between 16 and 17%. So right now, we see evidence that females tend to win the big money than what? Than males, okay? Ladies, pat yourself on the back. But yes, we see that evidence here, right? So I may want to determine whether or not do females tend to do better in playing the grand game than males. Is everybody with me so far? That would be an example of test of homogeneity. Okay? The word homogeneity, some people also pronounce it as homogeneity, same thing. There's 2 pronunciations of it. Homogeneity or homogeneity means same. Is everybody with me? In this case, it means same behavior. Okay? So in other words, according to the data, do we see the same behavior occur, or can we conclude the same behavior across these 2 groups? Is everybody with me so far? Does this show that, okay, the null hypothesis says it don't matter by by gender. You should have the same likelihood of winning the big money. Is everybody with me so far? Alternative hypothesis will be testing, well, do females tend to do better or males tend to do better? Okay? What that will say is if we reject the null hypothesis, that will tell us that the gender is dependent on the outcome of how much you win. Okay? But particularly what we will be saying is we will be concluding that depending on the gender you are, that will determine if you have a good chance of winning more or less money. Okay? That's what we're going to determine in homogeneity, the test of homogeneity. You can do that when one of your variables is a demographic variable. Is everybody with me so far? This is demographic. This is preset before they play the pricing game. You see what I'm saying? The game show don't assign gender. That's fixed. You see, that's a demographic factor. So we're comparing groups. That's test of homogeneity. You understand? And then later we're going to see, well, when can we look at test of independence? When both of those variables are determined by the researcher. None of them are demographic factors. Is everybody with me? Like gender is in this example. So test homogeneity, okay? We have a fixed independent variable. What do I mean by that? That's the same thing. Like this is fixed. Like I said, Price is Right, they don't determine gender. Is everybody with me so far? This is determined from playing the pricing game, right? So this is fixed, okay? Demographic variables are fixed, all right? So we are satisfying this condition. We have a fixed independent variable. We have a random dependent variable. What do I mean by random? We don't know how these contestants are going to win this amount of money until after they play the pricing game, right? So that's random. So the outcome here is random. Is everybody with me? The amount of money that they won is random. So that satisfies this condition. Our dependent variable is how much you won. The independent variable is what is your gender. Is everybody with me? No hypothesis says that these two variables are supposed to be independent. They're not supposed to have anything to do with each other. Which means that don't matter, male or female, you should have the same chance of winning, more money or less money depending on which side of the spectrum you're interested in. Are you interested in winning less money or winning more money? Of course it's going to be more money, okay? All right, so what's unique about this test is it's very similar to the ANOVA test. What do we do with the ANOVA test? With the ANOVA test, we could compare multiple groups, right? We could compare more than two groups. Now, in this example here, we only have two groups, unfortunately, right? We only have two groups, male and female. But let's say if we had, instead of looking at it by gender, let's say if we looked at it by age group. We had like young adults, middle adults, and senior citizens or something like that. So we had 3 rows, you understand? But we still have these same 4 columns here. Is everybody with me so far? Okay, we can still do the chi-squared test. We would still have a fixed rows, which are gender, and then we could have our random dependent variable, which is how much money they want. Okay, get back. Sorry. So this is similar to the one-way ANOVA test, but with a categorical dependent variable. Okay. All right. So what's good about the chi-squared test and the one-way ANOVA test is that both of those tests allow you to compare more than 2 groups. Both of those tests do have some post hoc analysis. The difference between those tests is this, okay? When we did the one-way ANOVA test, our dependent variable was quantitative. Here, it's qualitative, okay? So even though I know you're thinking, hold on, those are finite, those are dollar amounts. Dollar amounts are quantitative. You're right. But I'm using those dollar amounts as classes now, okay? These are actual classes. And I don't have to have dollar amounts there. I could have had, like, let's say we had a different pricing game. Won a trip, won a boat, won a car, won furniture. You see what I'm saying? You can have qualitative columns. It just so happens that the dollar amounts are going to be used in a qualitative fashion this time. Okay? All right. Getting back. I'm sorry? Oh, this variable here, the dependent variable, is qualitative when you're performing the chi-squared test. When you perform the one-way ANOVA test, this variable is quantitative. Your dependent variable is quantitative. All right, so here's the example we're going to use, okay? Different example. Okay, factor can create more than 2 independent subpopulations. So in other words, like I said, in the example earlier, we saw male versus female. We could have more than just 2 rows. We could have looked at like 3 rows, for example. And like in this example here, consider conducting a hypothesis test and compare how top winner contestants bid or pass on the first showcase, given the grand prize of the showcase. So in other words, this. Consider